Okay, so if you haven't picked up your exam, they're back here on this table. Anybody need their exam? No? All right, so let's real quick run through this. The class average on this test was an 80.57, and that was very close to the same average as on exam 1. We had 80.9, so right around an 81 average. Standard deviation was about 17 points, so I mean, it's almost like a mirror image of exam 1 in terms of average and standard deviation. The blue is exam 1, the orange is exam 2, so we had the same number of A's as we did on both exams. The number of B's dropped a little bit, the number of C's went up, the number of D's went down, the number of F's went up, okay? The green bar here is passing, so you can see a majority of the class passed both exams. And then we have kind of this is the danger zone right here. If you're down here in both both exams, then I guess it's time for you to talk to me about what you can do differently to prepare. But I can't force you to come to my office, right? I can't mandate that you come talk to me. I can only highly recommend that we get together and just discuss things. It's not too late, right? If you're over here, it's not too late to recover, but it's getting to that point. We only, I think, have 2 more exams. So overall, I think I said in my email I was very pleased with the results. It's a really good average for the test. I thought the test was sufficiently, I guess, challenging, I don't know. Highest grade was a 104, so yeah, good. Questions? Yes?
The orange is the second exam, right?
The orange is the second exam, yes. So you can see a lot of people kind of stayed where they were. There are a couple of, improvements here. These are improvements, right? It's good. Anything else? The way I graded the exam, just in case you're curious as to how I did it, each problem was worth 10 points. There were 14 problems, so there were 140 points possible. So, if you missed 20 points, you got 120 out of 140, and that's whatever percent that is, that's your grade. And I posted those online. I don't believe the grades are on here, right? The bonus was worth, I believe, up to 7 points. Did anyone get 7 points? I thought someone got 7 points. I don't remember if anyone got it completely right. I mean, I gave partial credit for it. Usually on bonuses, I only give credit if you get it completely right, but this one I decided to give partial credit for. Okay. Tests are on that table back there if you need your test. All right, so no questions, we're gonna move on, yeah? So as a quick warm-up, let me put something up here that we talked about last time, at the very end of class last time. We were still in this topic of implicit differentiation. So I had put this formula up on the board. PV equals nRT. Do you remember that? I started talking about this. I said one of the great things about implicit differentiation is it allows us to see how one variable changes with respect to the other ones. So one of the questions I could ask here is like dp dv. Okay, so I could say, let's find this. And what you would do here is you would treat v like the independent variable. So anytime we take the derivative of v, it's going to be 1. But if we take the derivative of anything other than v, it's going to be d, whatever that variable is, over dv. So let me just run through this. If we take the derivative of this, on the left side, we have to apply the product rule. So we'll do derivative of p, right? Let me write it this way. I'm taking the derivative with respect to v of the left side equals the derivative with respect to v of the right side. And remember from last time that the n and the r are constants. Okay, these are constants. The things that are variables are p, v, and t. All right. So the derivative of this, I'll have to use the product rule. What's the derivative of p with respect to v? dp over dv, and then times v, and then plus, now what's the derivative of v with respect to v? 1 times p. Okay, so that should be the derivative of the left side. And then on the right side, I have the derivative of this, but remember n and r are constants, so they're just going to come for the ride. N times r, and now I need the derivative of t with respect to v, which is dt over dv. All right? And what was it that we were looking for? dp dv, which is this right here. So now what we would do is just go through and isolate it. Right? We'd move this over, subtract the p. Let me just do it. Subtract the p on both sides. It's gone here. And then what would be my last step? Divide by v. Divide by v. That's gone. And so dp dv would be equal to this quantity. So if you knew all these values, you could figure out how fast the pressure is changing with respect to volume. Okay, another question I could ask would be let's say dp dt, capital T, like that. Okay, so we'll run through that real fast. The difference here, if I do derivative with respect to capital T of p times v equals the derivative with respect to capital T of nr capital T, the left side is going to be different now, right? So when we do our product rule, the derivative of p with respect to capital T would be dp dt, right, times v. Then plus, what's the derivative of v with respect to t? dv dt. And then times p to finish off the product rule. And then on the right side, same thing. nr is going to be here because it's constant. And then we do derivative of t with respect to t, and that time, this time that's the 1, right? Okay. One more. What is the derivative of v with respect to little t? Okay, I don't believe I did this last time. So what's different about this one? Little t is a variable that does not appear in the equation, right? Y'all agree? Yes. So since this doesn't appear in the equation, what we have to imagine is that the pressure, the volume, and the temperature in this equation are all somehow functions of little t. And think of little t as being time. So like maybe the pressure, the volume, and the temperature are all changing with respect to time. So we can still talk about how fast the volume changes with respect to time, even though time isn't in here. It's almost like a background variable. So when we do this differentiation, we follow the same procedure. The left side, our product rule. What's the derivative of p with respect to little t? dp dt, then times v, right? Plus derivative of v with respect to t, dv dt, then times p, that's our product rule finished off, equals, now constant again, n times r, and then times the derivative of capital T with respect to little t, dt dt, right? That is not 1, because these are two different things. Capital T is temperature, little t is time. So nothing goes to 1, does it? Nothing goes to 1. And that's perfect. This makes perfect sense when we're doing implicit differentiation. All right? Okay, let's get into today's stuff. We're going to be doing this. Basically this right here, with respect to time, we're going to be doing that a lot now. Whoa, 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 whoa. All right. There's a lot of words here, all right? So basically what I'm saying here is that welcome to related rates, the dreaded section, all right? Most students don't like this. I told you all about this already. And they don't like it because it involves word problems. And so half the problem is you just being able to set up the math correctly, all right? Interpreting the problem, putting down the correct equations and things like that. But it's the first real application of derivatives that we're seeing, like real world type thing. So we're gonna, unfortunately, with this topic of related rates, there's not necessarily a way you always do it. You know, like the product rule is the product rule, no matter what calculus class you're in, it's always product rule, right? Quotient rule is always the quotient rule. When it comes to related rates, there's not like a formal procedure that you always do. So what I have here, I say it's a procedure, but it's really just kind of like helpful like steps you should try, but not every problem is going to require these things happen. So let me just run through the kind of procedure first, and then it'll make more sense when we do some examples. So what we're going to want to try and do is maybe draw a picture of what's happening. So, and I should probably back up and think about, or tell you a little bit about what we're going to try and do. What we have happening in these problems is that things are changing. Okay, so you can think about, you know, when we first started talking about derivatives, we try to motivate it with the idea of someone like running and trying to talk about how fast somebody is going at a certain instant in time. You know, we talked at the beginning about, yes, it's easy to calculate average speeds, but what about the speed of something at an instant, right? And that became problematic because we got 0 over 0. Do you remember that? Okay, so with these problems, what we have are somehow these variables are related to one another. Maybe it's the PV equals nRT, pressure, volume, temperature, yeah. Maybe they're all connected to one another and they're changing with respect to time. And what we want to know is at a specific instant, how fast one of them is changing. Let me say that again. You have some equation that relates variables together and they're all changing. And what we want to know is at an instant in time, how fast one of them is changing. So when we draw a picture of what's going on, we want to draw a picture of the exact moment that we're talking about. So it's like a snapshot. Imagine something flying across the room, right? And you take a picture. That picture doesn't show it moving, right? A video would show it moving, but a picture is a snapshot. We're going to want to draw a snapshot at the exact moment that we're talking about. We're also going to want to draw a picture of the general situation, which means that we don't want to like lock any of the variables down. We want things to be able to kind of move and fluctuate. When we draw these pictures, we'll make sure we assign any variables, any constants. We'll want to label everything. Once we assign the variables, we want to write down, this is really important, what we're given and what we want, all right? What are we given and what do we want? And I'll explain that more as we go through the example. Once we figure out what we're given and what we want to try and find, we're going to need to somehow on our own come up with an equation that relates all the variables together. See, in general, we're not going to be given an equation in these problems. We have to come up with the equation. And then once we have that equation, we will do our implicit differentiation and then we'll solve for what we're trying to solve for. So these are the kind of the steps. I'll refer back to these in a moment, but they're on Canvas. You can print this out if you want as a guide. All right, y'all ready to get started? Okay, so these first problems that we're going to look at right here are not what we're doing today. This is just preliminary stuff. Like you should be able to do all of these problems without any calculus at all right? So this is not what we're doing, but let's make sure we can do these. These are just geometric ideas. Okay, so the first problem says, if the radius of the circle is 3 feet, then what's its area? Right? The radius is, I should have brought my little keyboard today. Give myself a little room. All right, so if the radius of a circle is 3 feet, then what's the area? So if I draw a circle, its radius is 3 feet. Is that circle moving? Is that changing? No, it's fixed, right? It's like a picture, snapshot. There it is, okay? If the radius is 3, we know the area. The area of a circle is always pi r squared, right? So the area of this circle would be pi times 3 squared, which is 9 pi. And in this case, it would be feet squared. Why is it feet squared? Because measurements of area are done in squared units. Okay, so that problem should be pretty easy for everyone in here. Okay, let's move to the next one. If the diameter of a circle is 2.5 feet, then what's its area? Okay, so what's different here? They're giving us the diameter instead of the radius, right? Okay, big deal. What's the diameter? How is it related to the radius? Yeah, so we know this formula, that's how we get area, right? But we also know the diameter is twice the radius, right? So for the area formula, we need to know radius, and we have diameter. So how would you go about this? I'm just curious. I mean, there's multiple ways to do this.
I would divide it to plug them.
You would just take the diameter divided by 2, and then plug that in over there? Do you all agree we could do that? All right. Could you do this? Just tell me if you could do this. Could you take this equation and solve it for r? Yes? And then come back to this equation and replace r with this expression. Okay? Let me just do that. I realize this may not be the most efficient way that you would do it, right? But I'm just asking whether or not that makes sense. That makes sense? So now I have a new formula, don't I? This formula is how you find the area of a circle if you're given the radius. This is how you find the area of a circle if you're given the diameter. So for us, we'll do area equals pi, and then I take the 2.5, I divide it by 2, and then I square that, right? And then whatever that is, blah, 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 that's our answer. Right? Okay, so the key to this one is just to understand that if your original equation has 2 variables, like a and r, if you have a relationship between r and some other variable, you can somehow replace it in here and now have a new equation with 2 different variables, a and d instead of a and r, right? We're going to be doing this later, so just to kind of get you thinking that way. Okay, now how about this one? If the diameter of a circle is 1 foot, what's the circumference? Well, first you need to know what the circumference of a circle is. So what's the circumference of a circle? 2 pi r, right? Okay, so you were given, I don't know who said that, but that's the final answer, 2 pi, but that's because the radius is 1, right? Oh no, sorry, diameter, sorry. Take that back, strike what I just said. This is the formula for circumference, yes? Okay, so we are given the diameter, right? So I could do the same thing, right? Same thing I just did. I could say, all right, diameter is twice the radius. Solve for r, that's d over 2, and then replace that in this formula. If I replace the r with d over 2, these 2's cancel, and you just get pi times diameter. Right? So again, a new formula, right? A new formula that has c and d in it instead of c and r. To answer the question, we would just replace this with 1? Yes, and we'd be done? Okay. All right, how about this one? If the circumference of a circle is 100 inches, what's the area? Ooh, okay, so this one's a little more involved, right? We're given the circumference, right, is 100 inches. And we want to know the area, right? So what I'd like for us to do right now is see if we can somehow come up with a formula on our own where it connects area and circumference together. So what we know is that area is pi r squared. That's the one we all have memorized, right? But I want area to be in terms of c, not r. So how can I get that? What do you know about circumference? Yeah, I can just take this formula for circumference, right? Solve for r. So if I solve for r, what's r? C over 2 pi, right? And now can't I plug that into that formula? Replace the r with c over 2 pi. So area is pi times c over 2 pi squared. Agree? And let me go ahead and square that. I'm going to square that. I mean, we have a formula. We're technically done, but there's some stuff that could clean up. If I square a fraction, I can square the top and then square the bottom, right? So I square the 2, I square the pi. And one of those pi's will cancel. This pi will cancel with one of those. So we get a final kind of result here. Maybe we could write like c squared over 4 pi. Right? So this is our new formula. There it is. That's not one that you see in the back of a book normally, right? Normally you see area is pi r squared, which is great if you know the radius. But this formula works if somebody gives you circumference. Give me the circumference, I will provide you the area now. Make sense? So to answer this question, what we do is just replace that c with 100, right? Square it, divide by 4 pi, that's your area. Any questions on that? Yes?
You don't cancel the pi's in the middle line because you're supposed to apply the second power first, right?
Yes, order of operations. You've got to do exponents before multiplication. All right, let's look at this last one here. I think this is the last one. If the area of a circle is 24 pi, then what's the circumference? Wait a minute, didn't we just have a formula that related area and circumference together? We just came up with it ourselves, didn't we? It was area was circumference squared over 4 pi. Here we're given the area, right? Could you solve that for C? Could you take that formula and solve for C? Okay, let's do it. So what would you do first? 4 pi on both sides, so you get 4 pi times A. That would clear out the fraction, right? 4 pi on both sides. And then finally, square root of both sides. So C should be equal to the square root of 4 pi times the area. Now, we're supposed to do plus or minus because we took the square root, right? But the negative won't make sense because circumference is going to be the distance around a circle, so we're going to chunk that answer, even though algebraically they're supposed to be a negative, right? So now this is our new formula. So why don't you have all these formulas in the back, like in your formula sheets? Why don't they give you all of these? You only need the basic ones, and then from that you should be able to generate all these yourself. I mean, that's the idea. You give you the bare minimum that you need to create formulas if you need them. So this is a new formula for circumference given the area. And this is for a circle. So replace A with 24 pi, plug it in, that's going to be your answer. All right. In all of the problems that we've just seen, I've been asking questions about finding area, finding radius, finding circumference, finding all these different things for a circle that is fixed, right? That's not moving, it's just there. Now we want everything to start moving. So I thought about which one I wanted to do first, and I've decided I want to do this one first. Yeah. So imagine that I took like a really thick oil or something, and I started pouring it out right here on the table. And we're looking from the top down. Okay, so I start pouring it out, and I'm going to pour it out at a constant rate. So the amount of liquid coming out is going to be the same all the time. What is going to happen when it hits? And forget the splashing and all that. Just imagine it. What are you going to start seeing on the table? A puddle, right? It's going to look like a what? Triangle? No? It's going to look like a circle, right? And it's going to start growing, right? So let's see what happens here. So that's what would happen on the ground, right? It's growing. So notice that as we continue to pour, it seems like it's growing very slowly right now. Now it's very slow, but watch in the beginning. It's going to start again. Look how fast it grew in the beginning, right? It's growing really fast. And the reason is, as you pour that liquid in, it's the same amount of liquid all the time, right? It's very easy to create these small circles because they have a small area. But if you stop, right, if you stop at some point, to move my radius out a little bit, right, from here to move it out, let's say to 6, I've got it, hello, okay. To move that radius out one more unit, right, I've got to fill in all of that space with liquid, yes? And that's a lot of space to fill in. But back in the beginning, right, if I'm like right here, and I want to increase it, right? That's a smaller area, so I need less liquid. So that's why in the beginning it grows so fast and towards the end it grows slowly. Do we all understand that? Okay, so what is the question that we are going to ask? What is the calculus part of this question? So what we're going to ask is this. We are pouring this liquid in, right? So that the area of this thing keeps growing at the same rate. Because I'm adding the same amount of liquid the whole time, so the area of it's growing at the same rate all the time. But the radius of the circle is not growing the same rate, right? It's kind of, if you just track the end of this, it's slowing down, right? That's getting slower and slower. Do y'all believe it's getting slower? You can see it right here. Look at the radius. When it starts over, watch how fast this number grows. There. So 1, 2, 3. See, it's getting longer. 4, right? So it's taking longer for that radius to grow. But notice that the area is just counting at the same rate the whole time, right? So the calculus question is this. We're watching it, and then we say, right, I don't know, let's just pick a point. Right there. Okay, so when I clap my hands right there, at that instant that I clapped my hands, I would like to know how fast that radius is moving. Okay, at that instant, right? In the beginning, we already said, in the beginning, the radius is going to move pretty quick, right? In the beginning, that radius moved pretty fast, and it's slowing down, slowing down, slowing down. It's still growing, but not as fast, so I'm saying at that instant, right there, what was the speed of the radius? Understand? Sure, this is the time to ask questions. Okay, so here it is. This is the way it would be presented to you in a problem. This is that problem without the pictures. If the area of a circle is increasing at a constant rate of 1/5 of a foot squared per second, so every second we are adding 1/5 of a square foot to that area. That's basically saying we're pouring it at a constant rate. Then how fast is its radius increasing when the area is 5 feet? So you've got this thing, it's growing, and then remember I said we're going to clap our hands, take a picture at that instant. That instant is right here. How fast is the radius increasing when the area is 5 square feet? The area of that circle is only 5 square feet one time, right? As it's growing, it's like at an instant it's that area, but then an instant later it's not that area anymore, right? All right, so let's try and follow the kind of template procedure. And if you're confused right now, let's just get through this first one, all right? So the first thing I'm going to do is I'm going to draw a picture of the general picture for what's happening, right? What I have here is a circle. That circle has a radius. I'm going to call it R. And that radius, is it changing? Yes, it's moving, right? In general, this circle is growing on the ground, right? My general picture always wants to let things move. I don't want to take my picture yet, okay? So the radius is changing, and that means the area is changing in this picture. Everything's moving, yes? Okay, the next picture I'm going to draw is the instant that we're talking about. In the instant that we're talking about, my circle is no longer moving, right? It's not changing. Because I'm interested, when I took the picture, what can you tell me about when we took the snapshot picture? Test is on that table. Is there anything you can tell me about the instant that's obviously going to be different from this picture?
The area is 5 feet.
The area of this one is fixed, right? This one, the area is 5 square feet. Okay? If the area is fixed, right? If the area is fixed, then what can you tell me about the radius? It's fixed, right? If I tell you the area of a circle is 5, that means you can tell me what the radius is. We just did that in the previous problems. In fact, we know that this radius, r, must be equal to, well, we'd have to go solve for it, wouldn't we? So I could say, okay, if area is 5, and I know area is pi r squared, must be 5, then r squared must be 5 over pi. And that means r must be the square root of 5 over pi. Understand what I'm doing here? I'm saying, look, at this instant, when the area is 5 square feet, I know that my radius has to be fixed at that number. I could fill that in here. All right. General picture, everything's in motion. This picture we snapped. And that's what's happening when we snap the picture, right? Next thing I'm going to put up here is what I'm given and what I want. And I like to do these together. All right, so I'm given some information, right? On the given information, what you're usually looking for in these problems is a rate of change of something. How fast something is moving or changing. So in the word problem, which of those quantities that were given is a rate of change? 1 over 5 foot squared, right, per second. That's how fast what's changing. What? This is the rate at which the area is changing, right? Because square feet is a measurement of area, and this would be read square feet per what? Second. Second is a measurement of time. So the way I'm going to interpret this right here is as follows. I'm going to say that the rate at which the area is changing with respect to time, right? dA dt, the rate of change in area with respect to time is given to me to be 1/5 square feet per second. Do you see? I'm interpreting that number up there as a derivative of something, as a rate of change of something. Why am I using little t here? Time, right? Second, per second. Miles per hour would also be like d something dt. All right. What is it that you want to know? What is it you're being asked to find in this problem? How fast? Wait a minute, fast. Fast is speed, right? Speed is derivative, yes? You're asked to find the derivative of what? The radius with respect to time. So how fast is the radius increasing? So what should I put here? I want dr dt, right? I want dr dt. How fast is the radius changing with respect to time, right? That's what I want. So I'm going to put a question mark next to that. That's what I'd like. Now, there's one more additional piece of information in the part that we want. Not only do we want to know how fast the radius is changing with respect to time, we want to know how fast it's changing with respect to time at a specific moment in time, right? So I want this when? At the moment that the area is 5. Or I could put at the moment that r is square root of 5 over pi. Either way. This is generally what we're going to do for all of these problems. We're going to have a general picture where everything's changing. An instant in time. What we're given, what we want. All right? I think that's pretty sufficient for us to move to the next step. And the next step is really, they're all critical steps, but this one's absolutely critical. What you need to do now is you need to look at the variables you have here and here. And when I say that, I mean, I want you to look at this variable here, a. Okay, and I want you to look at the variable here, r. Now, area, radius, circle, right? Can you come up with an equation that has area and radius in it in terms of a circle? Any equation you can come up with that has area and radius in it. Okay, so my next step here is to come up with an equation. Okay, my equation must relate these two variables together, and you all said area is what? Pi r squared. Now, one person and one person only volunteer to tell me why I needed to come up with an equation that had capital A and little r in it. Who wants to tell me why I'm doing this? Go ahead.
Because they're given dA over dt and you're looking for dr over dt. So
Okay.
you need a formula that relates them.
So it relates those area, but why? What am I going to be able to do with this?
You're going to solve for the derivative on the equation.
Okay.
You'll input whatever you're given, so 5, and then you'll be able to solve for dr dt.
Okay. Good. That's good. You want to elaborate?
I was going to say you need to make the A cancel first. And then you need the R you have.
What do you mean make the A cancel first?
Because when you take the derivative, if you took the like dA dt,
Uh-huh.
that would make it, A will go to 1.
Yeah, so, well, with respect to T, though.
Well, A will go to 1/5. That's what I'm saying. If you took D over dt.
Okay, yes, exactly.
A will go to 1/5. And then the R, you already know what you can play.
Okay, good. Any other elaborations? Okay, those were good answers. I'm going to kind of polish it off. We want to know about how fast area is changing with respect to time, right? We know. I'm sorry. Yeah, we know this. Sorry, we know how fast area is changing with respect to time. We want to know how fast radius is changing with respect to time. From the previous problem that we did when we started class, we saw that if we have an equation that relates variables, we can always differentiate with respect to little t and get things, right? We get all these dvdt's and dpdt's and all these things come in when we do implicit, right? So if I have an equation right here that has capital A and little r in it, I know right now that if I differentiate this with respect to little t, this guy and this guy are going to appear, right? These two things are going to appear when I differentiate this. And I will have a new equation that includes the things I'm trying to solve for. So I'm creating this and forcing this to happen, if that makes sense. So this step, we have the equation. Next step is take the derivative with respect to little t, all right? So now I take the derivative with respect to little t. My marker's dead. Oh, I should also point out, because this is a major bad step. At this point right here, when you get the equation, you are not allowed to go and replace A with 5. All right? You cannot do this yet. And the reason why is because as soon as if you were to say right now, hey, I'm going to replace A with 5, what you're doing is you're stopping the circle from moving. You're taking the picture. It's like me showing you a picture of someone running and saying how fast are they moving. You can't answer that question because you've stopped everything's motion. By leaving A as a variable right now, I can take the derivative and it's treating it as if it's in motion. Does that make sense? Okay, so let's do this now. Derivative with respect to time on the left side. Derivative with respect to time on the right side. Pi r squared. Okay. I think it's sticky time. Jasmine? Following? Okay. So what is the derivative of A with respect to t?
It should be dA over dt.
dA over dt. Okay, good. Equals, all right, do you want to keep going?
Sure. Is it d pi? Is that?
Pi is a constant, right?
Yeah.
So just
But
bring it down.
Okay, so then pi 2r.
2 times 2r, almost there. One very important thing left, Jasmine.
Is it dr?
It is, dr dt. So we have chain rule happening here, right? The pi is a constant, comes for the ride. Derivative of r squared is 2r, but then chain rule says derivative of the base, which is dr dt, because it's with respect to t, not r. So we have dr dt. Right? Now, Jasmine, do you see how important it is that you remember the chain rule here? Because if you forget the chain rule, you don't ever have a dr dt. And isn't that what we want? And it would never appear, right? But because we know it has to appear, because that's the whole idea here. If r and a are in here and we differentiate correctly, we will always get a dr dt and a dA dt somewhere in our equation. At this point, we can take our picture. We can snap the picture now, and we can answer the question. All right? Only after the differentiation can we finally figure it out. So dA dt, we're happy to see it because we know what it is, right? Pi is a constant. 2 is a constant. What about the radius? Do we know the radius at this snapshot picture in time? Yeah. Square root of 5 over pi. We know that now, don't we? And do we know dr dt? We don't know it, but that's what we're trying to solve for. So this is the thing we're looking for. We know everything else. We know that. Well, pi we know, 2 we know, and r we know. So now I'm just going to plug everything in, and we'll be done. So I'll put that right here. dA dt, left side is what? 1/5 equals pi times 2. I'm going to write 2 pi times square root of 5 over pi, and then times dr dt. Everyone see where everything came from there? Also, on my 1/5, I didn't put like square feet per second. I didn't put any units here, right? I didn't put like, this right here is actually feet because it's the radius. I'm not going to include any units until the very end when I answer the question. All right, we get to figure out what the heck this is.
Divide over that.
Pardon?
Divide over that.
Yeah, you could just divide all this to this side, right? I'm actually going to clean this up a little bit first. I'm just going to do a little bit of work on this. I'll just do it on the side here. This is 2 pi times root 5 over root pi. I split up this thing, split it up. And I only did that because this over this simplifies. So when you do this with that, that becomes a square root of pi on top. So pi over the square root of pi is the square root of pi. And I can put those two together, right? I can put those two together. So now next step, what I'll do is I'll divide both sides by 2 square root of 5 pi. And I already had a 5 over here. You know what? Don't want to lose everyone. Okay, so that's what the right side is. Now I divide both sides by this. And when I do that, I get 1 over 10 square roots of 5 pi equals dr dt. And that is our exact answer. What do I mean by exact answer? Exact answer as opposed to approximate answer. So like let's say you were solving an equation, you got this answer 1/3. That's the exact answer. If you get the answer and you put 0.33, 3, and you stop right there, that's an approximation because you've stopped your decimals. Now if you put the bar here, that's also the same as this. But if we want a decimal answer for this, it's going to be an approximation. I'm going to go ahead and do this on my calculator and see what it is as an approximation. But this is the exact answer. 1 divided by 10 times the square root. Where the hell is my square root? There it is. Square root of 5 pi. This is approximately, squiggly equals approximately 0.0252. I'll just go like that, 252. Okay, so now what I need to know is what are the units on this? What is it?
Feet per second.
Feet per second. Why?
Radius is in feet times
All you have to do is look at this ratio here. This is the ratio of how fast the radius is changing with respect to time, right? How do we measure radius? Feet. How do you measure time? In this problem, it was what? Per second. So this is going to be feet per second. You have this circle, right? You're pouring in this liquid. Right? You're pouring this so that the area grows at a constant rate. At the exact moment the area is 5 square feet, at that exact instant in time, the radius is growing at a rate of 0.0252 feet per second. An instant later, that's different, right? An instant later, that value is going to be different. A second later, it's different. 10 seconds later, it's different. So you might be asking, like, why would you even want to know, right? How fast the radius of this circle is increasing at a certain point, right? Yes? I mean, I think that seems plausible. I can give you like just a first thing that comes to mind. This was our first example, so this is a pretty basic example. But let's say you have a lake. And let's say you have a dam right here, right? Okay, this is not a good picture. But you have a lake and it's got water in it. And let's say that the water is about to come over the dam, all right? We've got a lot of flooding, a lot of things. So the water's about to come over the dam. So this is where all the water is going to come over this dam. So what you can do is this can turn into a related rate problem. What you can do is try and figure out how fast the water is going into the lake, right? So you try and somehow measure the water coming in from the different streams and rivers and stuff like that, or feeding the lake. And then what you can do is you can figure out this right here, the stuff coming in, would be your dV dt. You figure out how fast the volume is changing with respect to time. And then based on the geometric shape of your dam, does it look like a funnel, or is it more like straight down the sides? You can actually figure out how fast the water level is going to come up. And what you can do is you can say at the instant that it breaches the dam, right, how fast is that water coming up? And if you know how fast the water is coming up, then you're going to know how fast that water is going to come over, and then you know whether or not people downstream are going to survive that or not. You know what I'm saying? Like if it's coming in very slow here, then this relationship, you may say, okay, we're fine. It's not coming in fast enough, the water's going to come out, and it's not going to wipe everyone out down there. These are related rates. You have to know how fast it's coming in. You have to know the shape of the container, right? And that will dictate how fast things are related to one another. I hope that kind of makes sense. Another example would be like if you have a piston in an engine, it's attached to, what do we call this thing here? I know there's got to be some people here who are engine people. No? Piston rod? No? Piston rod, crankshaft, cams on top. Crankshaft's on the bottom. Okay, so basically what you have is an engine, the way an engine works, I mean, we're not going to get into the details, okay? We're not going to start going through a schematic of an engine here. But you basically have a cylinder here, and you have a piston inside of it. Gas and air mix, spark, explosion forces this piston down. That piston pushes the rod. The rod is attached to a circle, and that point moves along here. So what you have is this thing goes basically like this. Okay, like this, and it turns linear motion into circular motion, and that allows you to drive, right? But as this piston's moving, what you can do is you can figure out if this explosion causes that piston to move down at a certain rate, so that, let's say, the change in height of that piston at any instant, you can measure it at an instant. You can say, okay, if it's coming down and at a certain instant, it's moving at a certain rate, you can figure out how fast then, at that instant, the angle is changing on this crankshaft. So you can find relationships between the speed of that and how fast things are going to turn. Am I kind of selling you on this a little bit? I mean, everything, anything that you could ever relate to another variable, anything, you can study how fast one thing is changing with respect to the other. All right. For us in this class, we're going to do examples that seem somewhat trivial, not trivial, but seem useless. Okay, I will admit that. A lot of these problems are going to seem useless. But the process, the procedure is what's important here. And then later on in a specific physics class or in a specific engineering class, it doesn't matter what it is you're talking about, as long as you understand that you can always relate the variables together and use implicit differentiation to figure out the relationships. All right? Okay. Now, we're going to look at a different problem. Still doing a circle. I'm just going to play this one, and I'm going to see if you can tell me the difference between this one and the previous one. I'll give you a hint. Something is changing at the same rate all the time. This time it's the radius. So notice the way this, so you remember the first one was pouring in something? Just wipe that out of your mind, okay? Let's just say we have a circle and we have this relationship that the radius is just growing at the same rate. See, this is not slowing down. It's not slowing down. It's just the same rate. You can see it in here. We count the radius, it's on the same count the whole time. But what about the area? Is the area changing at the same rate the whole time? Look at that area. Look how fast it's counting right now. Okay, let's see in the beginning. What happens to the area in the beginning? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Is it speeding up a little bit? It is speeding up. So even though the radius is changing at a constant rate, the area is not. Previous example was the reverse. The area was changing at a constant rate, the radius was not, right? So I switched things here. So let's take a look at the actual wording of this problem. If the radius of a circle is increasing at a constant rate of 0.5 feet per second, then how fast is the area increasing when the radius is 4 feet? General, instant, what we're given, what we want, equation. It's kind of your general template for all of these. All right, Ian? Ian here? No Ian? Jesse? What's my general picture? What am I going to draw a picture of here?
The radius of the circle.
Okay. So just a circle, right? And this thing has a radius, and everything's changing, right? Okay. So I'm just going to leave it like that, right? Radius changing, area's changing. Now in my instant picture, that's when we take our snapshot. Can you tell me about anything, Jesse, in the picture at the instant? Something that you know is true at the instant.
It's going to be bigger than the general. That's the part of the picture.
We don't really need to worry about drawing these to like scale. We just need to know this one's in motion, this one's not. This one's frozen at a point in time. Can you tell me anything about that point in time?
The radius is now 4.
The radius has to be 4, right? And that's given to us from this right here. So here the radius is 4 feet. And the radius here is 4 feet. And if we know the radius, we can get the area, right? I'm not going to necessarily put it in here. I could if I wanted to, but I'm just going to do it like that, all right? Okay, Marissa, what are we given in this problem? The rate at which the radius is changing. Does everyone see that? If the radius of a circle is increasing at a constant rate is derivative, rate of change, right? At that. So what do you want me to write here for given? dr dt
Equals
0.5 feet per second. Everyone okay with that? Marissa, what do we want?
D8.
How fast, right? That means they want to know a rate of change of something, the rate of change of area, right, with respect to time. So they want, you said what, dA dt? We want that. Is there any particular moment in time when we want that?
When the radius is 4.
So at the moment that the radius is 4. Okay? Owen. Where's Owen? Owen. Understand so far?
Yes.
Okay. We ready for the equation?
Yeah. So then
What two variables are you trying to relate together with the equation?
the area and the radius.
The area and the radius.
So it's just like the opposite of the equation last time.
Well, does the equation last time have A and R in it? That's all we need. So you can use the same thing. Doesn't matter. As long as it has capital A and little r, our equation could be exactly the same. Okay? Pi r squared. Now what? Derivative with respect to little t, right? So derivative with respect to little t of A equals derivative with respect to little t of pi r squared. Is this derivative any different than the one we just did in the previous problem? No, this is exactly the same derivative. It's just what we're given and what we want have changed places, right? So the left side of this is what? dA dt. The right side of this is 2 pi r dr dt. Right, so we've already done that. Pi came down, 2 came out. I've just cleaned it up. Okay, when we get to this point, I like to just check everything. dA dt, are we happy to see this? Yes, because that's what we want, right? How about 2 pi? It's a constant. Okay, how about r?
Yes.
We know r, right? R is 4. So we're going to be able to replace that with 4. And then what about dr dt? Well, that's 0.5. So we can now plug everything in. Remember, though, when you're at this point right here, never plug anything in. All right? Never plug anything in. Always wait till after the differentiation. So dA dt is what we want. Look at that. We don't even have to solve for it. It's already there, right? 2 pi, r was 4 times dr dt, which was 0.5. I'm going to put a half here. So what does this turn out to be? 4 pi. 4 pi, don't say anything. Al? 4 pi what? 4 pi what? What are my units? Did I catch you off guard there?
So this is area, so it's going to be
Feet squared
per second.
per second. Everyone agree? So to get this unit thing, I always just like to figure out what all the numbers are, and then when you get the units, just look at what these two things are. Area over time, area is squared units, time here is seconds. That's the exact answer. If we get our calculator out, we can get an approximate answer. Make sense? Okay, you ready to change it up? We need something else. We can't just do circles all day long. All right, let's take a look at this one. I'm going to just leave this stuff up here because I think I'm going to read. Well, I'll erase it. I don't mind writing while you're reading. Example, an expanding sphere. Sphere, not circle. If the radius of a sphere is increasing at a constant rate of 2 feet per second, then how fast is its volume increasing when the volume is 36 pi cubic feet?